All right, so we just finished talking about the process of how capillary electrophoresis works and how the STRs are passed through a laser detector and recorded on a graph. And so here's what you get as a printout from the genetic analyzer. The genetic analyzer is the machine that the capillary electrophoresis happens in. You get a printout that looks like this, well, similar to this. So this is one of the STRs and all of the different options it could have. So at the D3 location, you can have 1, 2, 3, 4, 5, 6, 7, 8 different types of repeats, between 12 and it looks like 19 repeats. And you get these little spikes in the graph. Here is another STR and where it would print out. Here's the Emil one. You can tell that this person is male because they have an X and a Y chromosome. If they were female, they would just have one spike here because they'd be female. Here's another STR, another one, so on and so forth. And these little spikes just are all the locations that are possibilities for a short tandem repeat. So take a look at this one because I feel like this is a little more actual. This is somebody's DNA profile and you can see at this particular STR, this person is heterozygous, meaning they have two different types of alleles. One was 15 and it looks like one was 19 repeats. Okay, here is another STR. This person was heterozygous here as well, 17 and 18 repeats. Here's another one. This person was 19 and 25. So that's 3 STRs and the alleles that they had at each one. Now notice over here, this person has only one X. It's because they're homozygous, meaning they technically have 2 X's. It's a female, right? But the spikes are directly on top of each other. Okay, so you can't see it. So if you only have one peak, that means a person's homozygous, meaning that they have 2 of that exact same allele. Okay, so here's another repeat. Here's another one. Here's another one. So far we have 1, 2, 3, 4, 5, 6, 7 STRs that they've ran. Okay, here's another one. And this one, they're homozygous, right? So this one is 12 and 12 because 12 is the only one that shows up. So they got a 12 repeat from their mom and a 12 repeat from their dad. Here's another one, and then here's another one. So this particular genetic analyzer printout had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 STRs ran in it, okay? And then you could figure out what STRs they were based on where they were located, and then you can figure out how many alleles that person has at each STR. So like at this one, the person was 17 and 19 repeats. It always kind of puts the number right underneath it. Okay, so that's how you read a genetic analyzer printout, is you take a look at where the spikes are. Do you have 2 spikes? That means the person's heterozygous. They have 2 different alleles. If there's 1 spike, it means they're homozygous and it's 2 of the same alleles. And so you just read the genetic analyzer printout, and then you're able to compare that genetic analyzer printout to somebody else's, and if they have the same alleles at the same STRs, it's the same person, and if they don't, it's 2 different people. The last thing we're going to talk about is mitochondrial DNA. It's the same idea as STRs, except the mitochondrial DNA only comes from your mom, and so in order to do comparisons, so say that they were going to run mitochondrial DNA on me, they would only be able to compare it to my mom and or my grandmother. So a lot of times they use mitochondrial DNA in like missing person cases if they're wanting to try to figure out if the person is a family member or something like that. The issue with mitochondrial DNA is it's hard to work with, it's expensive, so the only reason that they really ever use it is if for some reason they cannot get nuclear DNA. The nuclear DNA is too degraded over time, or they don't have it available for some reason. Otherwise, they don't usually use mitochondrial DNA. It's not a common practice, but I do like to let you guys know. And they do the same thing. They go through exactly the same process. It's just they can only compare it to the mom's side of the individual, which is why it's a little more challenging to use. That's it. So just a quick recap with all of this, right? Just to make sure that we're all 100% on the same page with everything. For your process of DNA profiling, right? Step 1, release the cells. Step 2, add the PCR primer so that they find and locate the STRs that you're wanting in your DNA, right? And then they go through the polymerase chain reaction and copy just those locations in your DNA. And then that goes into the capillary electrophoresis machine, the genetic analyzer. And this is what a genetic analyzer looks like right here. Okay? The genetic analyzer has the capillary electrophoresis machine inside of it, right? So they insert the DNA here, it runs through the capillary tube using electricity, and it goes by the laser detector. The detector detects the fluorescent primers that were added during PCR, and it creates a printout that you are able then to read.